Hello everyone, Assalamu alaikum. Welcome back for another video in the series. In the previous video, I showed you how the softmax regression model looks like. Now let's talk about the multi-category cross-entropy loss that we will need for training such a model. And for that, we will also need a one-hot encoding scheme for representing the class labels in a way that is compatible with the multi-category cross-entropy loss. So this is just a recap of the slide I already showed you in the previous video. It's how the basic setup looks like, where we have an input feature vector and then we have a multiple set of weight vectors. If we have age classes, we have age weight vectors, which we combine into a matrix W. So we discussed that before, and I don't need to recap this, I think. But what we are focusing now is how we compute this softmax activation part that comes from these different net inputs. So here's an overview of how the softmax activation function looks like. It's fundamentally not very complicated. It's essentially a normalization function. It's in a way you can think of it as a generalization of logistic sigmoid function for making the probabilities to sum up to 1. So let's say we have a class labeled T. So the possible class labels are 1 to H, and with the softmax activation, we can compute the probability that a given output belongs to a class T. So if I go back here, this is Z1, Z2 up to ZH. So we have H inputs here. And from that one, we can compute this one, which is essentially the probability that the class label belongs to class 1, like A1, given the input vector. And how this works is there are two parts. It's essentially an exponential function. So you have e to the power of net input as the numerator. So I is the index over training examples, and here in the denominator we sum over all exponential terms. So we have these exponential terms j, also 1 to h. And if we have h class labels, we have h activations and obviously h net inputs. So here we are summing over j. So this is essentially a normalization term. If we apply this, the probability will be smaller than 1, between 0 and 1, and the probabilities from all the net inputs will sum up to 1. So consequently, if I go back one more time here, so of all these should be 1 after this normalization function. So this is essentially how this softmax activation works. Now let's talk about the loss function. So before we talk about this loss function, there is one more thing. We have to talk about OneHot encoding, which is an encoding scheme for categorical variables. And we can also apply this to the class label variable. So you can use that in different contexts. You can do that for encoding features. You have probably seen that in the context of traditional machine learning, but we can also apply this OneHot encoding scheme to the class label variable or the class label vector, which is essentially also categorical variable. So imagine we have a data set that consists of different class labels here. Each row represents one training example. So we have the first training example with class label 0, the second one with the class label 1, and then the class label 3, and then class label 2, and the possible class labels are 4. Now um, we have these possible number of class labels as 4. We can convert this into a OneHot encoding on the right hand side here. So we have now a column for each possible value. So class 0, 1, 2, and 3. And each row still represents one training example. So here, this is still the first training example. The second row is the second training example. The third is the third. And then there is the fourth. So this still refers to training examples 1, 2, 3, and 4. And then we can look at all these 4 features here. So uh, training example number 1 has class label 0. So it has 1 and indicator 1 in the column class 0, and all other columns are set to 0, as you can see. So here this is a 0 0 0 because it's class 0. So the true class has 1 in its particular position, and the other ones are all zeros. And consequently, if you look at training example 2, this one has class label 1, and it has a 1 in the second column belonging to class 1. And then let's do one more. So training example, this belongs to class 3. It has 1 here in the last column. So this is how the one hot encoding works. You can think of it as an indicator variable. So you have like a 1 in the right column, and the other ones are zeros. And here's now how the multi-category cross entropy looks like for the different class labels. So if class labels 1 to h, and essentially it's a generalization of binary cross entropy. So if you recall, the binary cross entropy is essentially the negative log likelihood. Now, if you recall, what we had was then this negative log of the activation. That's the same thing here. So we also have a negative log, but there is one more thing. Now we have this yj here, and the yj is either 1 or 0, right? According to the one hot encoding that we just studied. So this is either a 1 or a 0. So this whole equation assumes a one hot encoding. I will show you a concrete example in the next slides to further clarify that. But just to focus in on this overview here, also I again is over the training examples. So let's only focus on this inner term here. So what we have is we have for this y either 1 or 0. And then we are summing over these negative logs for these different activations. So each activation is a value between 0 and 1. So we apply, it should be actually larger than 0. So we apply minus log of this term between 0 and 1, and then we sum over all of these for the output node. So we have h output nodes, and we sum over those. So if we use the one hot encoding scheme, we have h classes, but only one class. The true class label for one class is only 1, right? According to the one hot encoding scheme, all the other ones are 0. And I will clarify this with a concrete example, because I think it's hard to visualize if you don't have a concrete example in mind. But one more thing here is that this first sum is then summing over all the training examples. So here's just the analogy to the binary cross entropy at the top. So at the top, you have the binary cross entropy. Here you have also the negative term. Bring it inside if you like. So you have this negative term, negative log likelihood, and this term is essentially the same as this term. If the class label is 1, right, and this one is when we had the class label 0. So if we have a class label 0, then we have 1 minus 0, then this is 1. So essentially we have also this term here, 1 minus a. We don't have that here at the bottom. Here we have a minus log of for all these classes, but essentially it's the same thing. It's just a generalization, because if we have a 0.8 here, for example, for the activation, then we would have a 0.2 here for 1 minus the activation, right? Because they have to sum up to 1. We set with a softmax function, it's the same thing. All the activations sum up to 1. So if we have two class labels, 0 and 1, these equations are identical, because it's just a different way of writing this here. We write this as the sum, but the sum is for binary classification, because basically the sum between these two terms. So it's essentially exactly the same thing, but now with writing it like this, using the one hot encoding, we can generalize this to more than two classes. I hope you get that. So here's a concrete example that I was talking about. Let's consider this example where we have 4 training examples. Each row here represents one training example, number 1, number 2, number 3, and number 4. And the column index represents which class label it is. So we have 3 possible classes, as you can see. So the first column is class 1, then this is class 2, and then this is class 3. So we can see class 1, the true label is class, training example 1. The true label is class 1, because the 1 is in the first column. This one has the 1 in the second column, so it's class 2. This should be class 3, because the 1 is in the third column, and this is also class 3. Here on the right hand side, I generate some arbitrary softmax outputs. So notice that all the columns should sum up to 1. You can double check that with calculator if you like. They should all sum up to 1 because we have mutually exclusive classes. This is what we get when we apply softmax outputs. I will also show you a code example how we can actually compute that in PyTorch, but let's continue with this example. So now let's compute the loss. So here at the bottom, so we are focusing on, let's say we are focusing on the first training example number 1. So this corresponds to this first row in the activation matrix. And now what we are computing is we are computing the negative log of the activations. So we compute 1 times the log of 0.37 and then 0 times the log of 0.31 and 0 times 0.31. So this is what I have written down here as well. So minus 1 times log of 3, 7, and then the other terms here. So this is this one here is that we are computing when we are summing. So for the first training example, we get a loss of 0.969692 like this. So this is our loss for the first training example only. Okay, I hope that makes sense. So we can do the same thing for the other training examples. So here I use a different color for each training example. Each color represents computations for different training examples. I don't have to go over the computations again, I think, because it's the same thing as we have done for the first training example. So you can go ahead, pause the video and verify that. And then one more step, we can put everything together. So now the outer sum, we are summing over all these losses here. And then we take a mean over n for all the training examples. And so the mean is 0.93. Otherwise, the sum would be 4 times of that. So usually, like I said, it's more stable in a deep learning context. In practice, if we compute the mean instead of the sum for mini batch, because then it's easier to find a good learning rate. Because let's say you find a good learning rate for a given mini batch, and then if you take a mini batch 10 times larger, the loss will also be 10 times larger. So you have to decrease the learning rate by a factor of 10 to get approximately the same performance. So it's usually I find it easier to deal with the mean instead of the sum. Okay, in the next video, I'll show you a code example of how that's done in PyTorch. I hope this was helpful. If you have any questions, drop them in the comment box below. I'll see you in the next video.